In this video, we'll consider another important idea of using Ampere's law, and this important case is one of what's called an infinitely long solenoid. If you put a series of coils back to back, close together, then you can make the field lines of the magnetic field go very long distances in a straight line before they loop around. This means that the magnetic field is intensified in the center here, and it's very little magnetic field on the outside. In the video that you're about to see, I will show you that you can actually drive a current through a loosely coiled solenoid, and you will see it deflect the compass, showing that we have a magnetic field that is directed along the center of the solenoid. We see the compass pointing, and as we move it around, it continues to point toward the north. This is because there's no current going through the solenoid. We will now turn the current on, and we see that the needle is moved, indicating there is a magnetic field produced by the solenoid. Current going through a solenoid creates a magnetic field that is strongest in the middle of the solenoid and points down the solenoid's main axis. We can see ours is not infinitely long, as it has curving at the edges. We'll now turn off the current, and the field is only due to the earth. Now that we know that the direction of the magnetic field lines are along the center of the solenoid, we can use Ampere's law to determine the magnetic field strength. The path that I'm going to choose for my measure of Ampere's law is the following path. I'm going to go along the field lines in the long solenoid, go up, and come back around. So my path has four parts. Path 1, 2, 3, and 4. I'm going to sum up the parallel part of the magnetic field times delta L, and that's going to equal mu naught times I that penetrates. So let's look at each one of these. There are four parts to this sum. Along part 1, I've got B, and B is directed along my path, so the angle is 0, so the cosine of 0 is being 1, and this distance is the length of the solenoid, which I'll call big L. So this is path 1. I then need to add that the contribution on path 2, but on path 2, the B field here is perpendicular to my path, and the cosine of 90 is 0, and as we go along the path, say these different points here, if this is an infinitely long solenoid where the B field keeps going on forever, by infinitely what we really mean is that it doesn't curve much. The field, it is very long compared to the width, so the field lines don't curve very fast, then there's almost no field out here. So we have B parallel delta L2, but the B field is basically 0 along that path. Then we have this path along here, B parallel delta L3, but again, there is almost no field out here if this is a tightly wound solenoid. You'll notice in the video that was not the case, that there was some curvature of the field. That's because those were loosely looped, not tightly looped like a really good solenoid would be. So this field should be 0. And then last, for the same reason as path 2, we get no contribution to the fourth part of my path. So I only get a contribution in here if this was this ideal infinitely long solenoid. This is equal to mu naught, and then I have to calculate the amount of current that penetrates the path. Now here's the point. You got to count up all the current. Each one of these loops, as they loop around, is carrying a current I. So there's a current I, there's another current I, there's another current I, there's another current I, so on and so forth. If there are N loops, there are N currents of I. So B is equal to N mu naught I over L. This is the length of the solenoid. The number of turns and the current. Now this is usually simplified into a little bit easier formula, although I don't really like it as well sometimes. Mu naught little n, where n is the turns per meter, and it's simply, little n is defined as big N divided by L. So it's not the number of turns, it isn't the length that's important, it's the number of turns divided by the length. That is how tight you wrap a solenoid. Now, you might ask why to build something like this. You can make the magnetic field be bigger by increasing the current, but when you increase the current through a wire, you will naturally cause increased heating because the wire has resistance. If you make it tighter wrapped with more turns, you get a bigger magnetic field for the same current. This means that you can make a very strong magnet while not having extreme heating or power loss due to the resistance of your wire. And that's why people like this device. So this is an extremely useful device. It's useful in creating large magnetic fields, and you can use those magnetic fields to pull switches, to start motors, and do other things, such as the coil that you have usually in cars, at least older cars, for starting your engine, or starting your engine for firing your spark plugs. Now, there is a disadvantage of this design, and that is no such thing as an infinitely long solenoid. So no solenoid is exactly perfect. All of them curve and have fringing fields, but you can make them a pretty good size where you can put stuff inside it and do magnetic field experiments. And so solenoids are a major part of science and engineering. All right, see you on another video.